So last time, if you remember, and I think I posted this video, we derived Gibbs equation. We defined free energy, which is delta, which is capital G, and free energy change as delta G. And with the definition of free energy, we were able to relate entropy of the universe to free energy. And that's what that equation does. One important thing to remember is that entropy of the universe, the change in entropy of the universe, has to be positive for a process to be spontaneous. But for free energy change, because of the definition, free energy change, delta G, has to be negative for a process to be spontaneous. So that's where we're going to start here. And I'm going to start with just conceptually with how you interpret delta G. Okay, so
that's a little high.
Oh, thank you for letting me know that.
Thank you.
Okay, there you go. So delta G is free energy change. It is, sometimes it's called a chemical potential, and it can be kind of understood as the potential energy that a chemical reaction contains before it goes to products, at whatever point you're considering. So it could be the potential energy you have in a chemical reaction before anything reacts, or even along the way as a reaction occurs, what kind of a potential is there. So it's related to energy. In a chemical reaction. A good way of thinking about it is to use an example of where delta G might actually be used in a practical application. And a really good practical application of this is when you're thinking about batteries. Batteries are little things, little units that contain within themselves a chemical reaction. That's how we get electricity out of a battery. A chemical reaction takes place in which electrons are transferred. And we'll talk more about that in the next chapter. But let's say you have a fully charged battery. You have in there a chemical reaction with, for the most part, all reactants. So no products have been produced yet. So you have the maximum amount of potential you could get from that battery, from that reaction that's going to take place. So the delta G would be at its greatest value. And then as the battery is being used, the battery gets drained and the potential energy goes down. So you have less and less energy to do something with. So that's a kind of a good way of thinking about what delta G means, is with that application of a battery. Now, delta G itself, though, for you to know that a reaction is going to occur, the value of delta G is more negative the more spontaneous something is. delta G is negative for a spontaneous process. I'm just going to see how this, I want to see if this is helpful. I'm going to try to draw like a picture of a battery before and after it's discharged. So let's say we have over here a new battery. Okay, so let's say it's got a little thing there. You haven't used it at all, and so maybe it's the copper top battery. If we look at its possible its possibility of giving you some energy, we can look at a diagram that has free energy on the left axis, and up here at the top you'd have an energy level that would correspond to the battery being new. Down here you'd have an energy that would correspond to the energy being old, the old battery. In other words, as it's discharged. Again, I think we're probably more familiar with the word dead when we refer to batteries being old. So let's say here it's a dead battery. Okay. So here you have a free energy that's higher than down here where it's been discharged, it's dead. The gap between those two lines is the delta G. Delta G is final minus initial. So going down would be your delta G value, and it would be negative. Because if you were to go down to where the battery was dead, you're at a lower energy, so you're losing that potential energy. That's why it's going to be a negative number going from here to there. That's kind of a way of thinking about it as well as graphically. If we're up here, then we have that far to go. We have that much to use. Now that's for a new battery. If the battery wasn't new, if it had been used a little while, but it wasn't dead, let's say it's been used, then the top line isn't as high. The bottom line's still where it would be if it was dead. Now the line has gone down a little bit, so maybe we're down here. This would be the used battery. It's been used a little bit. Our gap is smaller, so our delta G is not as negative. It's still negative, but it's not as big of a negative number. Okay, so that's the idea of thinking about it in terms of delta G being a potential energy. It's really a chemical potential energy. Okay. Any questions on that? This isn't even really an analogy, it's an actual description of reality. Okay, that really is the situation inside batteries.
Does it work the same with rechargeable batteries?
Yes, exactly the same. The only difference in a rechargeable battery is that you're working with a chemical reaction that's reversible, where there's arrow going both directions.
Oh, all
Batteries
right.
that aren't rechargeable can still have a reversible reaction, but the problem is the products that are produced in a non-rechargeable battery aren't in a form that they're still available to undergo the reversal. Think about a car battery, okay, like a 12 volt car battery, lead acid battery. Would you consider a car battery to be rechargeable?
Yes and no.
Well, yeah,
Yes.
it has to
Yes.
be. Otherwise, your alternator in your car wouldn't be able to keep it charged. Yeah, car batteries are an example of a reversible, of a rechargeable battery. It's just that they're not the little cells. The reason they're rechargeable is because everything you need to reverse the reaction stays in the car battery. It's in those little cells. So each cell in a car battery has liquid in it, has solid that's being produced as the reaction proceeds, and that solid then can go back into solution when you recharge it. Same thing in a little small, like a NiCad battery or some other kind of rechargeable battery. The products are in a state that allows the reaction to go in reverse. But with the throwaway batteries, the products can't go that way because they're no longer in contact with the solution in the same way that a lead acid car battery would be, or a rechargeable battery.
So why does rechargeable batteries, like at some point you cannot recharge them enough?
Just because the materials break down that's inside them. It all has to do with how because inside a battery you have things other than the reaction itself. You have layers of paper that separate the cells, and that paper can break down. It just wears out after a while.
Oh, all right.
Same thing with car batteries. Car batteries after a while don't hold a charge very well because the metal that's inside them eventually breaks down, and it gets oxidized, and oxidation of the metal inside is not the same reaction. It's a side reaction basically that you have that uses up the lead that's supposed to be part of the reversible reaction.
Oh, okay.
Yeah, but if it's rechargeable, that means you'd just be taking this line and you'd be moving it back up because you're pushing the reaction backwards. So the higher this line is, the more negative delta G is, and the more spontaneous it is. So that's another thing. Delta G is negative for spontaneous reactions, but the more negative it is, the more spontaneous the process is. Okay, so you can tell, kind of get an idea of how spontaneous a reaction is by how negative the delta G is. What if you're down here? What if our battery goes all the way down and reaches this line where you'd say it's a dead battery? What would the value of delta G be at that point?
Negligible?
0.
Negligible or 0? Yeah, it'd be very close to 0 or 0. When delta G is equal to 0, that's actually where we're at the equilibrium point. Okay, so that's like reaching equilibrium. And for reversible reactions, when they reach equilibrium, it's like the reaction has stopped because it's going forward the same rate as it's going backwards. So delta G equals 0 means that the reaction is not spontaneous in the forward direction anymore or in the reverse direction. Just add that here.
But so can a reaction be spontaneous in the reverse reaction?
Yes, it can. Yeah. A reaction, if the delta G is positive of a reversible reaction, that actually means that the reaction is spontaneous but in the reverse direction.
Okay.
But it has to be a reversible direction reaction for that. So delta G less than 0 means spontaneous. Delta G equals 0 means equilibrium. Delta G greater than 0 means the reverse is spontaneous.